Let us now consider some integrals involving hyperbolic functions that require the use of some identities. First, we have the definition of hyperbolic sine, which is equal to e to the x minus e to the minus x all over 2, and hyperbolic cosine x equal to e to the x plus e to the minus x all over 2. From this, we can also define our tangent, hyperbolic tangent of x, which is equal to hyperbolic sine over hyperbolic cosine. Equivalently, that is e to the x minus e to the minus x all over e to the x plus e to the minus x. As for the other three hyperbolic functions, hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent, you just take the reciprocal. We take the reciprocal to get the other three hyperbolic functions. The identities for trigonometric function, we have sine squared plus cosine squared equal to 1. But for hyperbolic functions, it will be hyperbolic cosine squared x minus hyperbolic sine squared x equal to 1. Before, we have 1 plus tangent squared equal to secant squared. For hyperbolic functions, it will be 1 minus hyperbolic tangent squared x equal to hyperbolic secant squared x. Hyperbolic cotangent squared x minus 1 is equal to hyperbolic cosecant squared x. This is analogous to 1 plus cotangent squared equal to cosecant squared. Hyperbolic cosine of x minus hyperbolic sine of x is e to the minus x, and hyperbolic cosine of x plus hyperbolic sine of x equal to e to the x. Now you can verify these two formulas by applying the definitions of hyperbolic cosine and hyperbolic sine. We also have the hyperbolic sine of 2x, which is equal to 2 sine hyperbolic sine of x plus hyperbolic cosine of x. We also have hyperbolic cosine 2x equal to hyperbolic cosine squared x plus hyperbolic sine squared x. For trigonometric function, cosine of 2x is cosine squared x minus sine squared x. So there is parallelism between this set of identities and identities involving trigonometric functions. Now, hyperbolic sine squared x is equal to 1/2 of hyperbolic cosine 2x minus 1. Before, for trigonometric function, sine squared x is 1/2 of 1 minus cosine of 2x. So again, see the similarity between hyperbolic functions and trigonometric functions. Hyperbolic cosine squared x is equal to 1/2 of hyperbolic cosine 2x plus 1. We have the following additional identities for hyperbolic sine of A, hyperbolic cosine of B, which is 1/2 of hyperbolic sine of A minus B plus hyperbolic sine of A plus B. We have a similar identity for this involving trigonometric function, right? We also have hyperbolic sine of A, hyperbolic sine of B equal to 1/2 minus hyperbolic cosine of A minus B plus hyperbolic cosine of A plus B. Finally, hyperbolic cosine of A, hyperbolic cosine of B is 1/2 hyperbolic cosine of A minus B plus hyperbolic cosine of A plus B. Okay, so these are important identities that will help us evaluate some integrand involving hyperbolic functions that cannot be evaluated using the fundamental formulas for hyperbolic functions. So let us have some examples. We evaluate the integral of e to the 2x hyperbolic sine of x dx. So notice that our integrand is a combination of an exponential function and hyperbolic sine of x. But we know that the hyperbolic function is essentially an exponential function. So we apply the definition for hyperbolic sine of x, which is e to the x minus e to the minus x all over 2 dx. Let us write down 1/2, and then we distribute e to the 2x. We shall be getting e to the 3x minus e to the 2x, e to the negative x, that will be e raised to x dx. We integrate this now, e to the 3x dx, which is 1/3 e to the 3x, and e to the x dx is e to the x plus c. We can simplify this by writing 1 over 6 e to the 3x minus 3 e to the x plus c. Another way of writing the final answer is 1 over 6 e to the x times e to the 2x minus 3 plus c. Okay? Next, we integrate hyperbolic cosine of x, hyperbolic cosine squared of x over 4 dx. This actually falls under case 2 for powers of hyperbolic sine and hyperbolic cosine. So the rule or the identity that we will use here is similar to the identity for trigonometric functions for case 2. No? We know that hyperbolic cosine squared x over 4 will be equal to 1/2 the integral of hyperbolic cosine of 2 times x over 4, okay, plus 1 quantity dx. So that is 1/2 the integral of hyperbolic cosine of 2x over 4 is equivalent to x over 2 plus 1 times dx. Then we integrate hyperbolic cosine, which is hyperbolic sine of x over 2. But take note, your u here is x over 2, and the derivative is 1/2, so you have to multiply it by 2. Plus, the integral of dx is x plus c. We can distribute 1/2 inside, so 1/2 times 2 is 1. Hyperbolic sine of x over 2 plus 1/2 times x, or x over 2 plus c. Let us evaluate the integral of hyperbolic sine cubed of x, and then the fourth root of hyperbolic cosine of x dx. Take note, hyperbolic sine and hyperbolic cosine appear together, and their exponents are 3 and 1/4. So take note, the power of hyperbolic sine is positive odd. So for powers of sine and cosine, it falls under case 3. So we shall apply the rule for case 3 and write this as hyperbolic sine squared x. We factor hyperbolic sine of x. Then the fourth root of hyperbolic cosine of x dx is equivalent to hyperbolic cosine raised to 1/4 of x. Then the other factor, hyperbolic sine of x dx. Since we have hyperbolic sine of x dx, let us express all the remaining factors in terms of hyperbolic cosine. And we will apply to hyperbolic sine squared x the identity. Our identity is hyperbolic cosine squared minus hyperbolic sine squared is 1. Okay? So we shall replace hyperbolic sine squared of x by hyperbolic cosine squared x minus 1. Hyperbolic cosine squared of x minus 1 times hyperbolic cosine to the 1/4 of x, hyperbolic sine of x dx. distribute. That will be hyperbolic cosine of 2 and 1/4. 2 plus 1/4 is 9 over 4 of x. Hyperbolic sine of x dx minus hyperbolic cosine to the 1/4 of x, hyperbolic sine of x dx. For both integrals, we will be using the power formula. Your u will be hyperbolic cosine of x, and the differential of hyperbolic sine is hyperbolic sine of x dx. So, for the first integral, it is actually u raised to 9 over 4, which will become u, or hyperbolic cosine. 9 over 4 plus 1 will give us 13 over 4 of x over 13 over 4 minus, for the other integral, you have the same set of u and du. That will be hyperbolic cosine raised to 1/4 plus 1 is 5/4 over 5/4 plus c, or 4 over 13 hyperbolic cosine 13 over 4x minus 4 over 5 hyperbolic cosine raised to 5 over 4x plus c. Let us do some simplification by factoring 4 over 65 and hyperbolic cosine to the 5/4 x. Okay, so that will give me 5. 65 divided by 13 is 5. Take away 5/4 from 13 over 4, that is 8/4. And 8/4 is equivalent to 2. So that is hyperbolic cosine squared of x. Then minus 65 divided by 5 is 13. We have factored hyperbolic cosine to the 5/4 x. So plus c. For the next one, let us evaluate hyperbolic tangent cube of 2y dy. For trigonometric functions, powers of tangent with an add exponent falls under case 1. No? Tangent with a positive integral exponent falls under case 1. So, the same thing for hyperbolic tangent cube. What is the rule here? We are going to factor hyperbolic tangent squared. So, hyperbolic tangent 2y, hyperbolic tangent squared 2y dy. And for hyperbolic tangent squared, we will be using the identity 1 minus hyperbolic tangent squared equal to hyperbolic secant squared. We shall write this as hyperbolic tangent 2y multiplied by 1 minus hyperbolic secant squared 2y dy. Hyperbolic tangent of 2y dy minus hyperbolic tangent 2y hyperbolic secant squared 2y dy. So the first integral is of the form hyperbolic tangent u. And what is the integral of hyperbolic tangent? That is ln of hyperbolic cosine of 2y, and because of 2y, the differential is 2 dy, so there will be a 1/2 in our answer. So for the next integral, we shall be using here the power formula, where your hyperbolic tangent is u and your hyperbolic secant squared is your du. So it only lacks 2 to complete the du, so we introduce also 1/2. So we'll be getting 1/2 and then power formula For hyperbolic tangent, it becomes hyperbolic tangent squared 2y all over 2 plus c. Our final answer will be 1/2 ln of the absolute value. Actually, there is no need of using the absolute value because hyperbolic cosine is always positive. So we can just write here the ln of hyperbolic cosine 2y minus 1/4 hyperbolic tangent squared of 2y plus c. We go to the next one, hyperbolic secant to the fourth of 5cdc. So for trigonometric function, if the power of secant is even, it falls under case 2. So the same thing for hyperbolic secant to the fourth, but of course we will be using a different identity. No? So we shall factor hyperbolic secant squared of 5c. Hyperbolic secant squared 5c dc. We know that hyperbolic secant squared is the derivative of hyperbolic tangent. No? So we have the identity 1 minus hyperbolic tangent squared equal to hyperbolic secant squared. So we shall replace the first factor, hyperbolic secant squared 5c, by 1 minus hyperbolic tangent squared of 5c times hyperbolic secant squared 5 of c dc. We now have two integrals, hyperbolic secant squared of 5c dc minus the integral of hyperbolic tangent squared 5c hyperbolic secant squared 5c dc. The first integral is of the form hyperbolic secant squared u. And the integral of hyperbolic secant is hyperbolic tangent of 5c. But our u is 5c, so du is 5dc. Thus, we will have 1/5 in our answer. Minus, for the second integral, we shall be using the power formula. Our u is hyperbolic tangent, and du is hyperbolic secant squared times 5. So, times 1/5. That will be negative 1/5. And u squared, the exponent here is 2. So u squared, that becomes u cubed. Hyperbolic tangent cubed of 5c all over 3 plus c. 1/5 hyperbolic tangent of 5c minus 1/5 times 1/3 is 1 over 15. Hyperbolic tangent cube of 5c plus c. Let us try hyperbolic cotangent cube of 2t and hyperbolic cosecant cube 2t dt. For trigonometric functions involving powers of tangent, cotangent, secant, and cosecant, if the power of cotangent is odd, it falls under case 4. We can apply the rule of case 4. So we shall factor cotangent and cosecant. It will be hyperbolic cotangent squared 2t, hyperbolic cosine squared 3 or 2t times hyperbolic cotangent of 2t, hyperbolic cosecant of 2t dt. And we will preserve this for our du. Okay? We know that this is a derivative of cosecant, hyperbolic cosecant, except that it should be negative. So everything here must be written in terms of cosecant. And what is our identity? What is our identity? Cotangent, hyperbolic cotangent squared minus 1 is hyperbolic cosecant squared. So hyperbolic cotangent squared 2t will become 1 plus hyperbolic cosine squared 2t times hyperbolic cosecant squared 2t hyperbolic cotangent 2t hyperbolic cosecant 2t dt. This becomes hyperbolic cosecant squared 2t hyperbolic cotangent 2t hyperbolic cosecant 2t dt plus the other integral cosecant squared, and cosecant squared is hyperbolic cosecant to the fourth 2t times hyperbolic cotangent 2t hyperbolic cosecant 2t dt. For both integrals, we will be using the power formula. So this is u to the fourth, and then this is our du. The missing term here is what? The derivative of hyperbolic cosecant is negative. So negative, and then times 2, so times 1/2. Okay? Same thing here. It lacks negative 2, so negative 1/2. Negative 1/2 for the first integral. U squared becomes u cubed. So hyperbolic cosecant cubed all over 3. Then negative 1/2. And u to the fourth becomes u to the fifth. Hyperbolic cosecant to the fifth 2t all over 5 plus c. We now write our final answer. Negative 1 over 6 hyperbolic cosecant cubed 2t minus 1 over 10 hyperbolic cosecant to the fifth 2t plus c. Let us try the integral of dy all over hyperbolic tangent to the fourth y over 2. Instead of using a negative exponent here, we use the reciprocal of hyperbolic tangent, which is hyperbolic cotangent to the fourth y over 2 dy. And this falls under case 1 for powers of tangent, cotangent, secant, and cosecant. So we shall write this as hyperbolic cotangent squared y over 2 hyperbolic cotangent squared y over 2 dy. And we will introduce the identity here to hyperbolic cotangent. We know that hyperbolic cotangent squared minus 1 is equal to hyperbolic cosecant squared. So hyperbolic cotangent squared y over 2 times 1 plus hyperbolic cosecant squared y over 2 dy. Distributing hyperbolic cotangent squared y over 2 dy plus hyperbolic cotangent squared y over 2 hyperbolic cosecant squared y over 2 dy. Once again, we apply the same identity to hyperbolic cotangent squared y over 2. So that becomes 1 plus hyperbolic cosecant squared y over 2 dy. Plus, for the second integral, our u is hyperbolic cotangent and our du is hyperbolic cosecant squared, but it must be negative. It must be negative. So negative, and then the derivative of y over 2 is 1/2. So it lacks negative 1/2. We multiply it by negative 1/2. for the reciprocal, which is negative 2. Alright? So we need negative cosecant squared for the derivative of hyperbolic cotangent, and we need 1/2. So we introduce 1/2 and we multiply it by its reciprocal. So it becomes now negative 2. It becomes negative 2 power formula. Hyperbolic cotangent squared becomes hyperbolic tangent cubed, y over 2 over 3 plus c. So we still have to evaluate dy, which is y, and hyperbolic cosecant squared is negative hyperbolic cotangent y over 2, but the derivative of y over 2 is 1/2. So we have to introduce 1/2 inside and multiply it by reciprocal 2. Then we just copy the last term, 2/3 hyperbolic cotangent cubed y over 2 plus c. And that is already our final answer. Okay, will you work on the following numbers? The integral of 1 plus hyperbolic cosine of 3m squared dm, the integral of 1 plus hyperbolic secant squared 2r squared dr, and the integral of hyperbolic tangent cube of alpha over hyperbolic secant to the fourth alpha d alpha. So this is hyperbolic tangent cube. So work on this and then I'll be back after 15 minutes.